NENOMATICA, where mathematics meets YouTube excellence. We will read the algorithm for square root inequalities, then apply it to a worked example. First, the problem header, and then the rule boxes. Step 1. Analyze the strict inequality square root of f of x greater than g of x. We use two cases exactly as the algorithm says. Case 1, g of x less than 0 and f of x at least 0. Case 2, g of x at least 0, f of x at least 0, and f of x strictly greater than g of x squared. Step 2, the non-strict version, square root of f of x greater than or equal to g of x. Again, two cases, but the last comparison becomes greater than or equal to. Step 3, solve each case as a small system and then take the union of both case solutions. Quick challenge. Predict which case the value x equal 1 will belong to. Now apply the rule to our example. Here f of x equals x plus 1 and g of x equals x minus 2. We follow the algorithm exactly in two systems. Case 1, g of x is less than 0 and f of x is at least 0. Solve and then intersect. Case 2, g of x is at least 0, f of x is at least 0, and f of x is strictly greater than g of x squared. Expand, gather terms, and solve the quadratic inequality. Compute the roots to find the open interval. Intersect with x at least 2. Finally, take the union of the two cases. Let us visualize the final answer on a number line and celebrate the result. The expression under the square root must be non-negative. So negative x squared plus 6x minus 5 is greater than or equal to 0. This is equivalent to x squared minus 6x plus 5 less than or equal to 0, which factors into left parenthesis x minus 1 right parenthesis times left parenthesis x minus 5 right parenthesis less than or equal to 0. Therefore, the radicand is valid for x from 1 to 5 inclusive. Now split by the sign of the right-hand side. When 8 minus 2x is negative, that is for x greater than 4, the left side is always non-negative and therefore strictly greater than a negative number. When 8 minus 2x is 0 or positive, that is for x less than or equal to 4, we can safely square both sides. Case A, if x is greater than 4, the right side is negative. Any square root is at least 0. So the inequality is automatically true. We only need to keep x inside the domain from 1 to 5. Intersecting x greater than 4 with the domain gives open 4 to closed 5. Case B, if x is less than or equal to 4, the right side is non-negative, so we can square both sides without flipping the inequality. This gives negative x squared plus 6x minus 5 is greater than the square of 8 minus 2x. Expand and simplify. Expanding the square gives 64 minus 32x plus 4x squared. Moving all terms to one side, we get 5x squared minus 38x plus 69 less than 0. Solve the quadratic inequality. The discriminant is 64, so the roots are 3 and 23 over 5. Because the coefficient of x squared is positive, the expression is negative strictly between the roots. Intersect this with x less than or equal to 4, and also with the domain from 1 to 5. We obtain the interval open 3 to closed 4. Finally, take the union of the two cases. Open 3 to closed 4, union open 4 to closed 5, equals open 3 to closed 5. Example, we will solve the inequality exactly following the structure shown on screen. Problem statement, solve the inequality. The square root of 2 minus x plus 4x minus 3 all over x is greater than or equal to 2. Step 1. Rearrange the inequality to isolate the square root term after multiplying by x, but remember we must split by the sign of x. In both cases, move the linear terms to the right. For x less than 0, we get square root of 2 minus x is less than or equal to 3 minus 2x. For x greater than 0, we get square root of 2 minus x is greater than or equal to 3 minus 2x. Step 2. Impose domain conditions. The expression under the square root must be non-negative and the denominator cannot be 0. That gives x less than or equal to 2 and x not equal to 0. Step 3. Case 1x less than 0. Here, 3 minus 2x is strictly greater than 3, and therefore positive. We may safely square after stating the non-negativity conditions. Step 4. Case 2x greater than 0. If 3 minus 2x is negative, the inequality square root greater than or equal to a negative number holds automatically. That gives the interval from 3/2 to 2. If 3 minus 2x is non-negative, we square to solve. Final step. Take the union of both cases. The solution set is the union of negative numbers with the closed interval from 1 to 2. Here is the example we will solve. The square root of open parenthesis 5x squared plus 10x plus 1 close parenthesis is greater than or equal to 7 minus x squared minus 2x. Step 1. Notice that 5x squared plus 10x plus 1 can be grouped as 5 times open parenthesis x squared plus 2x close parenthesis plus 1. Because the same combination x squared plus 2x also appears on the right, it is natural to substitute y equals x squared plus 2x. This turns the inequality into the square root of 5y plus 1 greater than or equal to 7 minus y. Step 2. We analyze by cases based on the sign of 7 minus y. Case 1. If 7 minus y is negative, which means y is greater than 7, then the right side is negative while the square root on the left is non-negative. Therefore, the inequality is automatically true for every y greater than 7. Case 2. If 7 minus y is non-negative, which means y is at most 7, we can safely square both sides to get 5y plus 1 greater than or equal to the quantity 7 minus y squared. Now expand and simplify the inequality. 5y plus 1 is greater than or equal to y squared minus 14y plus 49. Move everything to one side to obtain y squared minus 19y plus 48 less than or equal to 0. This factors as the quantity y minus 3 times the quantity y minus 16 less than or equal to 0, which gives 3 less than or equal to y less than or equal to 16. Intersecting with the case condition y less than or equal to 7, we get y in the closed interval from 3 to 7. Step 3. Combine the two sets. The union of D1 and D2 is open 7 to infinity, union closed 3 to 7, which simplifies to closed 3 to infinity. To visualize, here is a number line for y. The solution is every y at least 3. Step 4. Undo the substitution. Because y is at least 3, we have x squared plus 2x is at least 3. Move 3 to the left to get x squared plus 2x minus 3 is at least 0. Factor as x plus 3 times x minus 1 is at least 0. The solution to this product being non-negative is x less than or equal to negative 3 or x greater than or equal to 1. On the x number line, that means we shade to the left from negative 3 inclusive and to the right from 1 inclusive. Final answer. The solution set to the original inequality is all real x less than or equal to negative 3 or greater than or equal to 1. In this lesson, we will solve a radical inequality step by step and visualize the logic on a number line. The problem is square root of open parenthesis x minus 3 close parenthesis times open parenthesis x plus 1 close parenthesis is greater than 3 times open parenthesis x plus 1 close parenthesis. Step 1 is the domain. The square root requires the radicand to be non-negative. That means open parenthesis x minus 3 close parenthesis times open parenthesis x plus 1 close parenthesis is greater than or equal to 0. The critical x values are negative 1 and 3. The product is non-negative when x is less than or equal to negative 1 or x is greater than or equal to 3. Next, we split by the sign of the right-hand side, 3 times x plus 1. Case 1x plus 1 is less than 0, so x is less than negative 1. In this region, the right-hand side is negative, while the square root on the left is always non-negative. Therefore, the inequality is automatically true wherever the domain also holds, which is for all x less than negative 1. Case 2x plus 1 is greater than or equal to 0, that is x greater than or equal to negative 1. Intersect this with the domain x less than or equal to negative 1 or x greater than or equal to 3. So in case 2, we only need to check x equal to negative 1 and x greater than or equal to 3. First check x equals negative 1. then both sides are 0, so the strict inequality fails. Next, consider x greater than or equal to 3. Here both sides are non-negative, so we can square both sides safely. That gives open parenthesis x minus 3 close parenthesis times open parenthesis x plus 1 close parenthesis greater than 9 times open parenthesis x plus 1 close parenthesis squared. Since x plus 1 is positive for x at least 3, divide both sides by x plus 1 to get x minus 3 is greater than 9 times x plus 1. Solve the linear inequality to obtain x less than negative 3 halves, which contradicts x at least 3. Therefore, case 2 contributes no solutions. Let us display the final answer on a number line. The solution is all x less than negative 1, with an open circle at negative 1 because the inequality is strict. So the solution set is open parenthesis negative infinity comma negative 1 close parenthesis. Here is the problem. We want all real x such that the square root of the fraction x plus 3 over 4 minus x is greater than or equal to 2. We follow the standard structure. Let g of x equal 2, clearly positive. Let f of x equal the fraction x plus 3 over 4 minus x, which must be non-negative because it sits under a square root. This gives the preliminary domain from negative 3 to 4, including negative 3 and excluding 4. Let's visualize that domain on a number line. We shade from negative 3 up to, but not including 4. Because g of x equals 2 is positive, we can square both sides without changing the inequality direction. So we require f of x to be at least g of x squared, which is 4. Now solve the rational inequality. Multiply through and simplify to get 5x greater than or equal to 13. So x is at least 13 fifths. We still must remain in the earlier domain x less than 4. So together this gives 13 fifths less than or equal to x, and x less than 4. On the number line, the solution is the portion starting at 13 fifths inclusive and ending at 4 exclusive. Let's overlay it in green. Therefore, the final answer is the interval from 13 fifths up to 4, not including 4. In this lesson, we will solve a radical inequality step by step using a very clear case analysis. The problem is read as: the square root of quantity x plus 2 times x minus 1 is greater than or equal to 2 times quantity x plus 2. To organize our thinking, let f of x be quantity x plus 2 times x minus 1, the radicand, and let g of x be 2 times quantity x plus 2. We will use two cases, when g of x is negative and when g of x is non-negative. In both cases, the radicand must be non-negative. Case 1. If g of x is less than 0, then 2 times x plus 2 less than 0 gives x less than negative 2. Also, since there is a square root, f of x must be at least 0. That inequality, quantity x plus 2 times x minus 1 greater than or equal to 0, gives the union of intervals from negative infinity to negative 2 closed at negative 2 and from 1 to infinity. The intersection with x less than negative 2 is the interval from negative infinity to negative 2 open at negative 2. We will call this set D sub 1. Case 2. If g of x is at least 0, then x is at least negative 2. Again, the radicand must be at least 0. Because both sides are now non-negative, we can square safely f of x greater than or equal to g of x squared. That is quantity x plus 2 times x minus 1 greater than or equal to 4 times quantity x plus 2 squared. Expanding and simplifying yields 3x squared plus 15x plus 18 less than or equal to 0, which factors as 3 times x plus 2 times x plus 3 less than or equal to 0. Therefore, x lies between negative 3 and negative 2 inclusive. Intersecting with the earlier conditions gives just the single point x equals negative 2. We call this set D sub 2. Finally, the total solution set is D sub 1 union D sub 2, which is the interval from negative infinity to negative 2 closed at negative 2. In words, x is less than or equal to negative 2. Recap. We enforced the square root domain, split on the sign of the right-hand side, squared only when both sides were non-negative, solved the resulting quadratic inequality, intersected conditions in each case, and union the results. In this lesson, we will solve a radical inequality step by step. The inequality is square root of x squared minus 4x is greater than x minus 3. We will follow a clean case-based structure to match textbook solutions. Let f of x equal x squared minus 4x. Let g of x equal x minus 3. Because there is a square root, the radicand must be non-negative. F of x greater than or equal to 0. Factoring gives x times x minus 4 greater than or equal to 0. So the domain for the square root is the union of two intervals, negative infinity to 0, including 0, union 4 to infinity, including 4. Let us see this domain on a number line. We mark the critical points 0 and 4 and highlight where the radicand is non-negative. Next, we split into two cases using the sign of g of x. Case 1, g of x less than 0, that is x minus 3, that is x minus 3 less than 0, so x is less than 3. Together with the radicand domain, x belongs to negative infinity to 0, including 0. This entire case automatically satisfies the inequality because a non-negative square root is always greater than any negative number. Case 2, g of x greater than or equal to 0, that is x greater than or equal to 3, intersecting with the radicand domain, gives x in the interval 4 to infinity, including 4. For this case, we can safely square both sides. Now, we solve case 2 by squaring both sides. Square root of x squared minus 4x greater than or equal to 0, and g of x is non-negative, so we square to get x squared minus 4x greater than quantity x minus 3 squared. Expanding the right-hand side gives x squared minus 4x greater than x squared minus 6x plus 9. Subtract x squared from both sides, negative 4x greater than negative 6x plus 9. Add 6x to both sides, 2x greater than 9. So x is greater than 9 over 2. Intersecting with the case 2 domain 4, infinity gives d2 equals open interval 9 over 2 to infinity. Finally, we combine the two disjoint solution sets from the cases. The complete solution is negative infinity to 0, including 0, union, open interval 9 over 2 to infinity. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.